Welcome, discerning listeners, to another deep dive. Today, we're plunging into two worlds that, at first glance, might seem pretty separate. But as we unpack them, I think we'll find they're actually really deeply linked.
Yeah, definitely.
So on one side, we've got the meticulous craft of managing project data, kind of the unsung hero of any successful digital system.
Right?
And on the other, this revolutionary, but yeah, often mysterious realm of advanced AI models like the Transformer.
That's it.
We'll explore why understanding both isn't just technical. It's becoming absolutely non-negotiable for really anyone navigating our digital world.
That's exactly right. Our mission today, really, is to unpack how robust data storage isn't just like a nice to have. It's the absolute foundation. You can't skip it if you want successful system development.
Okay.
Then we'll journey into the fascinating complexities of modern AI, especially this black box challenge of explainable AI or XAI.
XAI, right.
And why going after that is so crucial for building trust, ensuring security, in this AI-driven world. And ultimately, we'll connect how all this impacts you, whether you're, say, building the next big app or just trying to make sense of the digital tools you use every day.
Okay, let's unpack this. Let's imagine we're building, I don't know, the next great AI-powered personalized health coaching app. So we're going to be dealing with mountains of sensitive user data.
Oh, yeah. Lots of it.
Our first source really stresses that data storage isn't just important, it's the bedrock. So for a project like our health app, or really any system, where do you even start? How do you get data management right from day one? What are the sort of human bits, the technical bits that set you up?
Well, what's fascinating and maybe a bit counterintuitive is that it all starts with discipline, like human discipline.
Yeah.
Because even with the best tech tools, you can just drown in disorganization so fast. Think about our health app. Tens of thousands of user files, maybe. Exercise logs, diet stuff.
Yeah, easily.
So first, file naming and classification. Sounds basic, but it's vital. You need descriptive names, project name, data type, date, version number, all in there.
Makes sense.
And a crucial tip, really, from the trenches. No spaces in file names. Seriously. Use underscores or, camel case.
Right. Avoid so many problems down the line.
Exactly. And consistent date-time formats. That's a must for version control, knowing what's what. Then you group the files logically, maybe by project stage, module, data type, or, importantly for our health app, sensitivity.
Okay, so sensitive stuff gets special treatment.
Absolutely. Extra security, tighter access controls. It's like I'm building a really meticulous library for your digital assets. You need to know where everything is and who can check it out.
That makes perfect sense for just finding things. I can just picture the mess if you don't do that from the start. But okay, once it's neatly categorized, the next hurdle is often making sure it's not like bloating our systems, right? And just as important, keeping it secure. How do we get smart about optimizing and protecting all this data for our health app?
Good question. That brings us to a few key things: metadata, compression, and of course encryption.
Okay.
So beyond just the file names, using metadata, that's like descriptive info about the data, who made it, what's in it, when it was created, that can vastly improve actually finding stuff and understanding the context. It's like the card catalog for your digital library.
Got it. The info about the info.
Precisely. And for tabular data, like maybe daily health metrics in our app, keeping order means breaking it down into smaller bits. Avoid redundancy, use relational databases, unique keys.
Okay.
And a key tip from our source: keep your raw data separate from your analysis results, your charts. Keep them clean.
Don't mix the original with the process stuff.
Exactly. And each spreadsheet should just contain one table. Simple rule, big impact. Always, always keep original versions of data, especially if you need to modify things. And use scripts for changes, so everything's traceable. Super critical for health data. You need that audit trail.
Right. Traceability is huge there. Okay, so that's organization and structure. What about the optimization part? Making it smaller, faster.
Right, so data compression. This can massively reduce storage space, speed up sending data, cut costs, and make backups way more efficient.
Sounds great. Is there a catch?
Well, yeah, there's always a trade-off, isn't there? Compression and decompression, they use up computing resources and time. So it's a strategic choice.
Okay.
We mostly see two types. First, lossless compression. Think ZIP files, GZIP, PNG images. It's like squishing a pillow into a suitcase. You can fluff it right back up, lose none of the fluff.
So you get the exact original data back.
Exactly. Crucial for text, program files, precise health readings in our app.
Mm,
Algorithms like Huffman coding, deflate, they're the workhorses here.
okay. And the other type?
That's lossy compression, used for multimedia JPEGs, MP3s, MP4 video. This gets much higher compression,
Mm.
but it does it by sacrificing less important data. Some info is just gone forever. Think of it like summarizing a really long story. You get the main points, but some details vanish.
Mhm.
Fine for maybe a user's profile picture, but definitely not their blood pressure history.
Right, you wouldn't want lossy compression on critical health data. Makes sense. And encryption, that sounds non-negotiable for a health app.
Oh, absolutely critical.
Yeah.
For protecting sensitive info, stopping unauthorized access, meeting data protection rules like GDPR or high pay, especially for our health app.
Yeah.
And encryption applies both when data is just sitting there, at rest on storage devices and when it's moving between systems data in transit.
Okay.
We use different algorithms. There's symmetric, that's like one shared key to lock and unlock the same box. Fast, good for big chunks of data. Think AES.
AES, right. Hear that a lot.
Then there's asymmetric. That's more like a secure mailbox.
Right.
Anyone can drop a letter in using the public key, but only you have the unique private key to open it.
Oh.
Crucial for setting up secure connections initially. RSA is a common one.
Okay, public and private keys.
Yep. And we also use hashing algorithms like SHA-256. These aren't really for encryption, but for verifying data integrity,
Yeah.
making sure nobody's tampered with those health records.
Like a digital fingerprint.
Exactly. So best practices, strong standards like AES-256 for encryption, TLS 1.3 for data in transit, really solid key management because losing keys is bad, and regular security checkups. It's your digital vault. Got to keep it secure.
Okay, so we've organized meticulously, we've optimized storage, we've locked it down with encryption. But, systems fail. Hardware dies, disasters happen, people make mistakes, especially with something as vital as health data. What's the ultimate safety net? What happens when things inevitably go wrong?
Yeah, that's a really important question. How do we make sure the data we've so carefully stored is actually accurate and available when we desperately need it? That's where storage validation and a solid disaster recovery DR plan come in.
Okay, validation first.
Yep. Validation is about ensuring accuracy, consistency, integrity. It helps prevent data corruption sneaking in. This means doing both physical checks, disk health, data transfer tests, error correction codes, and logical checks.
Logical checks, like what?
Like checking the data format is right, the values are what you expect, things are unique if they should be, and data is consistent across different systems. Basically, constantly double-checking your work, making sure the data makes sense.
Got it. And the DR plan.
For any serious project, especially our health app, a comprehensive DR plan isn't optional. It's mandatory. It's about minimizing loss and ensuring business continuity after, disruptions, hardware failures, cyber attacks, fires, floods, you name it.
So what goes into a good DR plan?
Key parts include risk assessment, figuring out what could go wrong, business impact analysis, understanding how bad it would be if it did, clear communication plans, who calls who when disaster strikes, and dedicated incident response teams.
And backups are central to this, right?
Absolutely. A core strategy here is the famous 3-2-1 backup principle. You need at least 3 copies of your data
3 copies.
stored on 2 different types of media. So not just 2 hard drives, maybe 1 hard drive and 1 tape, or cloud storage.
Right, different media.
And crucially, 1 copy kept off-site, physically separate from your main location.
Offsite. Got it. 3, 2, 1.
Exactly. And Cloud Disaster Recovery as a Service, or DRIS, is getting really popular for handling those off-site backups easily.
Makes sense.
It's also really important to distinguish between data backup that's mainly for short-term recovery, getting things back online quickly, and archiving, which is for long-term preservation, maybe for legal or historical reasons.
Ah, okay. Backup versus archive. Different goals.
Different goals, different retention periods, which leads to the need for a clear data retention and disposal policy. How long do you keep different data types? And how do you securely get rid of it when you don't need it anymore? It's all about building resilience right into the core of your operation.
So data management isn't just saving files. Wow. It's deeply foundational, incredibly detailed, and super proactive. It really does feel like this hidden bedrock that lets everything else actually work.
I couldn't have said it better myself. It really is.
Okay, we've spent a good chunk of time on this, invisible infrastructure of data management, and for good reason, it underpins everything. But what happens when that meticulously managed data meets, the cutting edge of computation?
The AI connection.
Exactly. Let's shift focus now to the fascinating, sometimes, perplexing world of advanced AI models. like the transformer, and how their massive data demands put even more pressure on those data foundations we just talked about. Our source mentioned the transformer model being used for something as practical as predicting customer churn. What exactly is a transformer? It sounds like something out of sci-fi.
Yeah, the name's pretty cool. But it's a deep learning architecture that really truly revolutionized the field, especially in natural language processing. It came out of Google Brain back in 2017. There was this groundbreaking paper called Attention is All You Need.
Attention is all you need. Okay.
And what makes it revolutionary is it mainly uses this mechanism called multi-head attention to process sequence data, like text.
Attention. How does that work?
Well, imagine you're reading a really long, complex sentence or paragraph.
Yeah.
Self-attention helps the model figure out which words or phrases are most important to each other, even if they're far apart in the text.
So it understands relationships across the whole sentence.
Exactly. It helps to build a much richer understanding of the entire context, rather than just, reading word by word linearly. It's like having this hyper-focused brain that really gets the nuances and connections.
Okay, that makes sense for language. But I'm still trying to wrap my head around how a model like that, designed for text, could predict something like customer churn for our health app. That feels like a huge leap from, say, translating French to English. How does it connect those dots?
Well, it's about how you represent the data. One practical application, like the one in our source, uses the past 90 days of customer transaction data. For our health app, this could be stuff like login frequency, how often they use certain features, maybe their premium subscription status, that kind of thing.
Okay, user activity data.
Right. They process this raw data using something called an RFM model. Heard of that?
RFM, recency, frequency.
Monetary, exactly. Recency, frequency, monetary. It extracts key features based on, when a customer last interacted or purchased, recency, how often they do it, frequency, and how much they spend, on average, monetary value.
Okay, so it boils down user behavior into these RFM scores.
Precisely. And these RFM features, these numbers, are then fed into the transformer model, often alongside other, maybe more established machine learning models like XGBoost. That's a gradient boosting method known for being really good at prediction, or even simpler neural networks like MLPs, just as a baseline.
So you feed these customer behavior summaries into different models.
And the goal is to predict customer churn. Basically, will this user stop using our health app or cancel their subscription?
Okay. So what does this mean for businesses trying to understand their customers? In the study you mentioned, did the transformer actually blow the other models out of the water on predicting churn?
Well, here's where it gets interesting. For the data set size they used in that particular study, somewhere between 10,000 and 100,000 records, the accuracy across all the models, including the transformer, was actually quite similar.
Oh, really? So no huge win for the transformer.
Not in terms of raw accuracy in that specific setup. Actually, TabNet had the highest F1 score, and XGBoost had the best overall accuracy.
Okay. So why bother with the complex transformer then?
That is the powerful insight from our source. Even with these relatively smaller, structured data sets, not massive text corpora, the transformer's self-attention mechanism means it can potentially self-attend to and identify the most important features from a huge number of inputs automatically.
Automatically. So less manual work.
Potentially, yes.
Yeah.
It could cut down significantly on the manual feature engineering grind.
Yeah.
Where data scientists spend ages figuring out which data combinations are predictive. Other models often rely heavily on that human expertise.
Right.
The transformer is more like this brilliant detective, automatically sifting through all the clues, all the input features, and figuring out which ones matter most without needing as much hand-holding.
Wow. Okay, that's a huge potential benefit, not just performance, but efficiency. Less human effort needed upfront.
Exactly. It's a potential game changer for how quickly you can build and iterate on models, even if the final accuracy isn't dramatically higher in some cases.
Yeah.
The development speed-up could be massive.
That's a really compelling point. But it also brings us right back to that crucial challenge you mentioned earlier, the black box problem. If our health app's AI tells a user, hey, based on your data, you're at high risk for condition X, we absolutely need to know why it reached that conclusion, don't we?
Absolutely do.
So why do we need this explainable AI, this XAI, if the models are already performing pretty well, maybe even finding features automatically? Isn't performance enough?
That raises the core question, doesn't it? Is prediction enough? And the answer, increasingly, is no. We need to understand the why. The fundamental issue with many complex AI models, especially deep learning ones like transformers, is their low interpretability.
They're black boxes.
Exactly. We don't fully get how they arrive at their decisions. We see the input, we see the output, but the process inside is murky.
Right.
There's this famous analogy, you might have heard it, about clever Hans.
The horse that could do math.
Sort of. He seemed to do math by tapping his hoof. But it turned out he wasn't actually doing arithmetic. He was just incredibly good at observing subtle, unconscious cues from the humans around him to know when to stop tapping.
Ah, okay. So he got the right answer, but for totally the wrong reason.
Precisely. And AI can do the same thing. It can give correct answers for the wrong reasons. There's a classic, almost funny example from our source about an AI that classified Pokemon images. It got like 98.4% accuracy. Amazing, right?
Yeah, that's incredible.
But why was it so good? Not because it recognized Pikachu or Charmander. It turns out most of the Pokemon images were PNG files with transparent backgrounds. When loaded, those backgrounds turned black. The other set of images, Digimon, were mostly JPEGs with white or varied backgrounds.
No way. So the AI just learned black background equals Pokemon?
It was basically cheating, using the background color as a shortcut. Now imagine that in our health app. What if the AI links high risk to, I don't know, the type of phone someone uses because of some weird correlation in the training data instead of their actual health metrics?
That would be disastrous.
Yeah.
Completely untrustworthy.
Totally. That's why we need both local explanations, like, why is this specific user flagged as high risk right now? And global explanations, what does high risk generally look like to the model across all users? What patterns is it seeing?
Okay, local for the individual case, global for the overall logic.
Right. It helps us build trust. It's a bit like that old copy machine study. People were much more willing to let someone cut in line if they gave any reason, even a flimsy one, like because I need to make copies. We crave explanation, even for simple things. For AI making critical decisions, we need explanations that actually make sense.
That's incredible and, frankly, terrifying. So these models can be fooled, or they find these weird unintended shortcuts based on artifacts in the data. Are there other security concerns with these black boxes, especially for something critical like our health app?
Oh, absolutely. This opens the door to things called adversarial attacks. And these can be really sneaky, often totally imperceptible to humans.
Adversarial attacks, how do they work?
Imagine taking an image, say, of a cat. The AI correctly identifies it. Tiger cat, 64% probability. Now, someone makes a tiny, tiny alteration to that image's pixels, adding a specific pattern of noise almost invisible to us.
Okay.
Suddenly, the exact same looking image is classified by the AI as a starfish with 100% certainty.
What? From cat to starfish, just from tiny noise?
Yep. Our source shows exactly that example. It can be incredibly minimal changes. Even altering just one single pixel in an image has been shown to shift an AI's classification from, say, a teapot to a joystick.
That's insane. A single pixel.
It exploits how the model understands patterns, often in ways we don't anticipate. And these attacks aren't just digital curiosities. They can happen in the real world, too.
Like how?
Imagine an autonomous vehicle's camera system. Someone puts tiny, strategically placed stickers or marks on a 35-mile-per-hour speed limit sign. To us, it still looks like 35, but the AI misreads it as 85 miles per hour because those subtle marks trigger a misclassification.
Wow. Okay, the implications for physical systems are huge. Self-driving cars, medical scanners.
Exactly. And for our health app, imagine someone finding a way to subtly manipulate the health data, a user inputs, or maybe even public health data sets used for training the model, causing the app to give wrong, maybe even harmful advice.
Yeah, poisoning the data itself.
Right. And these vulnerabilities can even be embedded during the training phase. These are called backdoors. Someone could subtly poison the training data so that the final model consistently misclassifies specific types of inputs later on, maybe inputs associated with the competitor's users or a specific demographic.
So the model itself has a hidden vulnerability built in from the start.
Potentially, yes. All of this means we absolutely need to develop robust defense mechanisms. Some are passive, like using filters to smooth out images or data to reduce the impact of these attack signals. Others are proactive, like adversarial training, where you deliberately train the model on examples of these attacks to make it more resistant.
So you teach the AI to recognize and ignore the trickery. Essentially, yes. It's like building up its immune system. It's a constant arms race, really, between attackers finding new exploits and defenders building better defenses to secure our AI systems.
Wow. Okay, so thinking about this whole conversation, the massive data requirements for these powerful AI models, combined with their their black box nature and this vulnerability to really sophisticated attacks. It just throws that critical connection back to our first topic into sharp relief, doesn't it?
It absolutely does.
Sophisticated data management. It feels like the more complex and powerful our AI gets, the more absolutely imperative it is to have those robust, clean, well-managed, trustworthy data foundations we talked about at the start.
Couldn't agree more. They're two sides of the same coin.
And the sheer cost, too. The cost of large storage, the high-performance computing needed for training these massive AI models. Our source highlights this, too, that ties directly back to needing efficient data practices like smart compression, good archiving, meticulous backups. It's all connected. Poor data management upstream leads to higher costs, lower quality data for training, and potentially more vulnerabilities downstream in the AI model.
Yeah, it really feels cyclical. Better data, better, more resilient AI.
Undeniably.
Mhm.
And, the true value here isn't just having the data or having the fancy algorithm. It's about understanding it, applying it responsibly.
Right.
That means constantly monitoring these AI models, especially as things change market conditions, user behavior. Their performance isn't static. It can degrade over time, drift, and they often need retraining on fresh data.
So it's not a one and done thing?
Not at all. It also underscores why you still need human expertise for that feature engineering we talked about, for interpreting the results, for ensuring strict compliance with data privacy regulations. And without explainable AI, without XAI, businesses run a huge risk. They might be making critical decisions based on insights they don't truly understand, or worse, insights that came from those weird shortcuts or vulnerabilities.
Yeah, flying blind, basically. For our health app, that could mean misdiagnosing someone, losing user trust completely, facing huge legal and ethical consequences.
Exactly. The stakes are incredibly high.
This deep dive has really highlighted how the future of building almost anything digital, whether it's a simple filing system or a cutting-edge AI health app, it really hinges on this dual mastery, doesn't it?
Hmm.
On one hand, the disciplined, meticulous management of huge amounts of often sensitive data, and on the other, a profound and increasingly transparent understanding of the complex AI models we build on top of that data.
That's the goal. When we combine that meticulous data hygiene, that really strong foundation, with the active pursuit of explainable AI, making those models less of a black box, we're not just building systems that are more robust or accurate. We're building a digital future that's fundamentally more trustworthy, more reliable, and ultimately, I think, more intelligent in the truest sense.
So here's a final thought to leave you with. If an AI can be fooled by a single pixel or by just the subtle change in background color, what does that imply about the really subtle, complex, nuanced cues it might be picking up or completely missing in the messy human data it processes every single day? Think about that the next time you interact with an intelligence system.